A neutral to ground voltage of 2.5 volts alternating current was measured, and this situation can indeed cause problems with sensitive electronic equipment, particularly satellite receivers and computer equipment. Here's a systematic approach to diagnose and resolve this issue. Firstly, isolate the receiver. Disconnect the satellite receiver from the power strip and measure the voltage between neutral and ground at the receptacle on the power strip. If the voltage drops to around 0.1 volts alternating current, the problem is likely related to the receiver itself or something it is interacting with. If the voltage remains high at 2.5 volts alternating current, the issue is upstream from the receiver, possibly in the power strip or the building's wiring. Secondly, check the power strip. Inspect the power strip for any visible damage such as frayed cords, loose connections, or signs of overheating. Unplug all other devices from the power strip and retest the neutral to ground voltage. If the voltage drops to 0.1 volts alternating current with all devices unplugged, then one of the devices you unplugged is introducing the voltage. Plug each device back into the power strip one at a time, testing the neutral to ground voltage after each device is plugged in. When the voltage jumps back up to 2.5 volts alternating current, the last device you plugged in is the culprit. If the voltage remains high even with all devices unplugged from the power strip itself may be faulty and need to be replaced. Thirdly, examine the wiring. If the issue is not the receiver or the power strip, the next step is to examine the wiring from the power strip back to the breaker panel. Look for any loose connections, damaged insulation, or signs of corrosion. Pay close attention to the ground wire connections, as a poor ground connection can cause elevated neutral to ground voltage. Check the tightness of the screws on the ground terminals at the receptacles, the power strip, and in the breaker panel. Fourthly, verify grounding. Ensure that the electrical panel is properly grounded. The grounding electrode conductor, typically a copper wire, should be securely connected to a grounding electrode such as a ground rod or the metal water pipe entering the building. A loose or corroded connection here can significantly impact the neutral to ground voltage. Fifthly, monitor voltage fluctuations. Since the problem seems to come and go, it's important to monitor the neutral to ground voltage over a period of time. Use a multimeter to take readings at different times of the day and under different load conditions. This can help identify patterns or specific times when the voltage is higher, which can provide clues about the source of the problem. Sixthly, consider shared neutral. In some cases, high neutral to ground voltage can be caused by a shared neutral circuit. This is when multiple circuits share a single neutral wire. If one of the circuits has a heavy load, it can cause voltage drop in the neutral, which raises the neutral to ground voltage on other circuits sharing the same neutral. Seventhly, check for harmonics. Nonlinear loads such as electronic devices, computers, and fluorescent lighting can generate harmonic currents, which can cause voltage distortion and elevated neutral to ground voltage. Harmonic filters or line reactors can be installed to mitigate these effects. Eighthly, contact a qualified electrician. If you are not comfortable working with electrical wiring, or if you have exhausted all of the above steps and the problem persists, it is best to contact a qualified electrician. They have the expertise and tools to diagnose and repair complex electrical problems. Ninthly, utility company involvement. If the problem appears to be originating outside of the building, such as with the utility transformer or the incoming power lines, contact your local utility company. They can investigate the issue and make any necessary repairs to their equipment. Tenthly, measure voltage at the panel. Measure the neutral to ground voltage directly at the main electrical panel. A reading higher than 1 volt alternating current at the panel indicates an issue with the grounding or neutral connections within the panel or upstream from it. Now, let's delve into some more specific steps and considerations to further refine the troubleshooting process. Confirm the integrity of the neutral conductor. The neutral conductor carries the return current from electrical loads back to the source. Any impedance in this conductor, such as a loose connection or corrosion, can cause a voltage drop, leading to an elevated neutral to ground voltage. Inspect the neutral connections at every point in the circuit, from the receptacle back to the breaker panel and finally to the neutral bus bar in the panel. Ensure all connections are tight and free of corrosion. Use an antioxidant paste on aluminum connections to prevent corrosion. Check the neutral bus bar. The neutral bus bar in the breaker panel is where all of the neutral conductors from the branch circuits are terminated. It is also connected to the grounding electrode conductor, which connects to the grounding system. Make sure that the neutral bus bar is securely bonded to the panel enclosure and that all connections are tight. Look for any signs of overheating or arcing on the bus bar, which could indicate a loose connection. Verify the grounding electrode conductor connection. The grounding electrode conductor connects the neutral bus bar to the grounding electrode, such as a ground rod or the metal water pipe. This connection is critical for providing a low impedance path for fault current to return to the source, which helps to protect against electrical shock. Inspect the grounding electrode conductor for any damage or corrosion. Ensure that it is properly sized according to the electrical code. Verify that the connection to the grounding electrode is tight and free of corrosion. Test the grounding electrode resistance. The resistance of the grounding electrode should be as low as possible, ideally 25 ohms or less. A high resistance grounding electrode can impede the flow of fault current, increasing the risk of electrical shock. You can use a ground resistance tester to measure the resistance of the grounding electrode. If the resistance is too high, you may need to install additional ground rods or improve the existing grounding system. Examine the branch circuit wiring. The wiring in the branch circuits that serve the satellite receiver and other electronic equipment can also contribute to neutral to ground voltage problems. Look for any damaged or improperly installed wiring, such as loose connections, nicked insulation, or undersized conductors. Ensure that all wiring is properly supported and protected from physical damage. Check for ground loops. A ground loop occurs when there are multiple paths to ground, creating a circulating current that can cause interference and elevated neutral to ground voltage. Ground loops are often caused by connecting equipment to different branch circuits that have slightly different ground potentials. To avoid ground loops, try to power all of the equipment in the rack from a single branch circuit. Use a star grounding configuration, where all of the equipment is grounded back to a common point. Consider using isolation transformers. Isolation transformers can be used to isolate the ground between different pieces of equipment, which can help to break ground loops and reduce neutral to ground voltage. An isolation transformer provides electrical isolation between the primary and secondary windings, preventing the flow of ground current between the two circuits. Monitor the load on the neutral conductor. Excessive current on the neutral conductor can cause voltage drop and elevated neutral to ground voltage. Use an ammeter to measure the current on the neutral conductor in each branch circuit. If the neutral current is excessively high, try to redistribute the load more evenly among the different circuits. Consider using a dedicated neutral conductor for sensitive electronic equipment. This can help to reduce the amount of current flowing on the neutral conductor and minimize voltage drop. Check for electromagnetic interference. Electromagnetic interference, or EMI, can also cause problems with sensitive electronic equipment. EMI can be generated by a variety of sources, such as motors, transformers, and radio transmitters. Shielded cables and filters can be used to reduce EMI. Ensure proper ventilation. Overheating can cause electronic equipment to malfunction and can also contribute to neutral to ground voltage problems. Make sure that the equipment rack has adequate ventilation to prevent overheating. Use fans or air conditioning to keep the equipment cool. Inspect the power quality. Power quality problems such as voltage sags, voltage swells, and transient voltages can also cause problems with sensitive electronic equipment. A power quality analyzer can be used to monitor the voltage and current waveforms and identify any power quality problems. Surge protection devices can be used to protect equipment from transient voltages. Now, let's talk about specific tools that may be helpful in this troubleshooting process. Multimeter or multimeter is an essential tool for measuring voltage, current, and resistance. A good quality multimeter with true root mean square or RMS capability is recommended for accurately measuring alternating current voltages and currents. Clamp meter. A clamp meter can be used to measure current without having to disconnect the circuit. This is particularly useful for measuring current on the neutral conductor. Ground resistance tester or ground resistance tester is used to measure the resistance of the grounding electrode. Power quality analyzer. A power quality analyzer can be used to monitor the voltage and current waveforms and identify any power quality problems. Thermal imager. Thermal imager can be used to detect hot spots in electrical equipment, which can indicate loose connections or overloaded circuits. Insulation tester. An insulation tester, also known as a megameter, is used to test the insulation resistance of electrical wiring. This can help to identify damaged or deteriorated insulation. Finally, it's important to follow safe electrical practices when troubleshooting electrical problems. Always turn off the power to the circuit before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Never work on electrical equipment when you are wet or standing in water. If you are not comfortable working with electrical wiring, contact a qualified electrician. Understanding the NEC or National Electrical Code is crucial. The NEC provides specific guidelines for electrical installations, including grounding and bonding requirements. Complying with the NEC helps ensure electrical safety and reduces the risk of electrical shock and fire. Article 250 of the NEC covers grounding and bonding requirements. Table 250.122 provides guidance on equipment grounding conductor sizing. Table 310.16 specifies allowable ampacities of conductors. Adhering to these standards is paramount. If the department store is large, consider the impact of long circuit runs. Voltage drop becomes more significant over long distances. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Use appropriately sized conductors to minimize voltage drop. For long runs, consider increasing the conductor size to the next available size to reduce resistance and voltage drop. Review the electrical panel schedule. The panel schedule provides information about the circuits in the electrical panel, including the circuit breaker size, the load served, and the wire size. Make sure that the panel schedule is accurate and up to date. Check that the circuit breakers are properly sized for the loads they serve. Overloaded circuits can cause voltage drop and overheating, which can contribute to neutral to ground voltage problems. Consider the type of loads connected to the circuit. Different types of loads can have different effects on the neutral to ground voltage. Linear loads, such as incandescent lighting and resistance heaters, draw current in a sinusoidal waveform. Non-linear loads, such as electronic devices, computers, and fluorescent lighting, draw current in a non-sinusoidal waveform. Non-linear loads can generate harmonic currents, which can cause voltage distortion and elevated neutral to ground voltage. Use appropriate filters or line reactors to mitigate the effects of harmonic currents. Evaluate the electrical system design. The electrical system design can also impact the neutral to ground voltage. A well-designed electrical system will minimize voltage drop, reduce harmonic distortion, and provide adequate grounding and bonding. Consider using a separate neutral conductor for each branch circuit. This can help to reduce the amount of current flowing on the neutral conductor and minimize voltage drop. Use the star grounding configuration, where all of the equipment is grounded back to a common point. This can help to avoid ground loops and reduce neutral to ground voltage. Review the facility's maintenance records. Maintenance records can provide valuable information about the history of the electrical system, including any past problems or repairs. Look for any patterns or trends that might indicate a recurring problem. Schedule regular electrical inspections. Regular electrical inspections can help to identify potential problems before they become serious. A qualified electrician can inspect the electrical system and recommend any necessary repairs or upgrades. Keep a log of voltage readings. Keep a log of neutral to ground voltage readings over time. This can help to identify any trends or patterns that might indicate a problem. Take readings at different times of the day and under different load conditions. Use the data to track changes and identify potential causes. Educate employees about electrical safety. Educate employees about electrical safety and the importance of reporting any electrical problems. Make sure that employees know how to identify and report electrical hazards such as frayed cords, loose connections, and overloaded circuits. Post electrical safety guidelines in prominent locations throughout the facility. By following these steps, the source of the neutral to ground voltage problem can be identified and resolved, ensuring the safe and reliable operation of the electrical system and protecting sensitive electronic equipment from damage.